Hi, everyone, and welcome to our webinar today. My name is Paul Bemis. I'm here with Bill Healy. We're going to be doing a presentation on the residential building sector. Before we get started and I do an intro here, I just want to tell you a little bit about this interface we're using. We're using something called GoToWebinar. And the way this works best is if you keystroke in questions into the questions panel as we go. I have two displays up. I'm going to be looking at your questions on one while Bill's presenting on the other. And that way we can make it more conversational. So please ask questions as we go. And I will try to interject them at the right point and make this more of a conversation than just a straight presentation in a sense of communication, back and forth communication. I'd like to also point out this will be recorded. We are recording today, and it will be available as an archive. Furthermore, Bill has already provided me a set of the material that he's going to be using today, and I will make that available to you. Those will come to you as a download. You should receive an email about a day after this event, and it will give you a link to watch the video recording again and or see the slides. So with that, let me introduce you to Bill. Bill is the Chief Building Energy and Environment. He's the Chief of the Building Energy and Environment Division at NIST. NIST is the National Institute of Science and Technology. And NIST is, of course, a government agency, and they are designed to promote American innovation and industrial competitiveness. I kind of like that. I've known NIST for many years. They're a science-based organization in the physical sciences laboratory, and they do a lot of interesting work. I've known them for many years, all the way back to my Hewlett-Packard days when we supplied them computing. Bill's background is in energy-efficient buildings, healthy and comfortable indoor environments. He has been involved with a variety of ASHRAE functions, including 4.4, 7.5, 6.6. So he's pretty well versed on what's going on in residential trends, the practices of HVAC, and what's going on in our residential side. And in that we are, in New Hampshire, a state with an awful lot of residential, and the need to move it towards a decarbonization future. It is an absolute perfect time to have Bill here. So welcome, Bill, to our event and to our presentation today. I have passed over to you the ability to present, and you should be able to share your screen now, Bill. Welcome to the program.
Great. Thanks, Paul, so much for that intro. Can you see my screen okay?
Not quite yet, and it could
okay.
be my fault.
1 second, I see what I got to do. All right, can you see that?
Okay.
Okay, thanks so much. I appreciate it. Thanks for that intro. As Paul mentioned, I do work at the National Institute of Standards and Technology, and I'll talk a little bit more about that just to kind of give you a little bit of background. But what I want to talk about today, and I really appreciate the opportunity, is ASHRAE and in general in the residential building sector. Now, why am I talking about this? In addition to a number of my duties with ASHRAE, I'm currently chairing the Residential Buildings Committee, and I'll talk to you a little bit more about what that's all about. But what we're really trying to, our goal with the Residential Buildings Committee is try to see how ASHRAE and position ASHRAE to serve the residential building sector. So now ASHRAE, you know, the thought is that they tend to focus on commercial buildings, and that makes sense because a lot of the people, a lot of the members really make their living with designing and helping out the commercial building sector, industrial building sector. So it totally makes a lot of sense. And if you maybe some of you out there might be involved in, say, multifamily, and certainly there's some design of multifamily and some efforts in those buildings. But you think about all the single family homes, they generally don't have the budget for each single family home to hire a design engineer, for example, to really, you know, analyze that. But there's still a lot of engineering science that does go into the residential building sector. So I want to talk a little bit about that and hopefully get a little bit of conversation going. One of our goals is the buildings committee residential buildings committee is to really get feedback from all stakeholders, and ASHRAE members are key stakeholders here on what ASHRAE should be doing in this sector. So the way I've outlined this, let me see here. Okay. What I want to talk about, it just generally give you some stats on residential building sector. You know, it's one of those things that maybe if we're not professionally involved in it, it affects all of us. You know, all of us hopefully have homes. And, you know, if you're like me, a lot of times I'll go to family functions and I'll get all these questions about, oh, you know, this isn't working and that's not working. And I scratch my head and sometimes I get frustrated knowing that I'm supposedly in this field and I don't have the answers for my family members, or I give them bad advice. And I think that, you know, putting more science and getting more resources available would be wonderful for all of us. So I want to talk generally about the residential building sector. Some of the challenges that, you know, for me, from my perspective and from hearing from the people what they're facing in the residential sector, I want to talk a little bit about research in residential buildings, and I'm going to pull mostly from our work at NIST, some of the, you know, one of our flagship projects, and talk about some of the stuff we've learned in that. And I think you might find it a little bit interesting. And then finally, ASHRAE and residential buildings, talk a little bit more about the Residential Buildings Committee and the resources that ASHRAE has available. And like I said, hopefully start a conversation to see what is really needed from all ASHRAE members in terms of residential. So now Paul touched a little bit on this, but I think it's good to give you a perspective of where I'm coming from. So I do work at NIST, National Institute of Standards and Technology. We are a federal agency. We're a part of the Department of Commerce, so we're not really focused on energy per se, like a Department of Energy, but we're really sort of, people call us the industry's national lab. So really we are focused on promoting innovation and industrial competitiveness. Our real big kind of our big claim to fame is this idea of measurement. So we are what's called the nation's metrology institute. So if you needed to know definitively how much a kilogram is, you would go to NIST, and NIST holds the nation's standard for a kilogram or a second or all other fundamental ones. So I'm more on the applied side, so we don't get down to that nitty gritty, but we do maintain standards for things in the building industry. For example, in my division, we look at thermal insulation. So if you wanted to go to the hardware store and buy R13 insulation, that's traceable to our labs, so that, you know, you can have confidence that you're buying an R13 insulation, and there's industry programs that trace back to our standards. So we, you know, measure things really well and send it to the test labs and say, okay, we're really confident that this is R13. You stick it in your instrument, and if you get R13, your instrument's working pretty well. So we do things like that, but this idea of measurement pervades everything we do, even if it's not a physical measurement. How do we measure performance? How do we measure indoor air quality, energy performance? And we work very closely with other DOE national labs. The other big piece is this idea of standards. It's in our name, standards. Now, you know, in the United States, most of our standards are industry driven. We don't want government driven standards. So we don't make our own standards, but we work with standards bodies like ASHRAE, like ASME, like ASTM, to try to work with them, because a lot of, especially in the residential building sector, there's a lot of small players. A lot of these smaller companies don't have money necessarily to send people to standards committees. So there's a lot of work that has universal benefits. So we'll try to do the technology behind that. So that's kind of really what our role is. We are, you know, these are just numbers, 3,400 federal employees. We are, you know, we have fundamental science too. We have a bunch of Nobel Prizes. I am located in Gaithersburg, Maryland. That's our main campus. We also have a pretty large campus in Boulder, Colorado, and a somewhat smaller one in Charleston, South Carolina, that does a lot of marine science. But Gaithersburg, Maryland is where all of our building work is located. We also, you may be familiar with things like the Manufacturing Extension Partnership, where they have offices in every state, and we really work with local small and medium manufacturers whenever they need some assistance. And this is run by NIST as well. And you may, you know, there might be, for example, small building product manufacturers, maybe in New Hampshire or wherever you may be listed. So these are, you know, it's pretty broad. We do a lot of things. Our laboratory programs, where I sit, you know, these, you know, as Paul mentioned, we do a lot of different stuff. I sit in the engineering lab there, that third one there, but those first two are sort of our primary measurement laboratories, material measurements and physical measurements. So physical measurement, for example, they would handle all of our, you know, length scales and time scales. Quantum science is a big deal now. So when you're getting down to the quantum scale, you look at that. Materials, if you needed material properties, there are some nice databases that are available. But I sit in the engineering lab, where we're a little more applied, and our focus is really on buildings, and manufacturing is really where our focus is. So I didn't want to give it advertisement, but I think it's valuable for you to understand where I'm coming from, where my perspective is, sort of in my day job. with that, let's jump into little stuff on the residential building sector. Give you, I like looking at stats and data and everything just to kind of give us some perspective on what we're dealing with here. I will give it a little bit of a U.S. focus, certainly, because basically the data is really good from the United States. Department of Energy, the U.S. Census Bureau really capture quite a bit of data on the residential building sector. So what are we looking at? We're looking at about 125 million occupied dwelling units in the United States. So that is, ranging from a single from an apartment with one person up to a single family house. So that whatever the family unit dwells, we're looking at about 128 million. So we have a country of what, 340 million. So we have a lot of housing units. About 64% of those in the U.S. are single-family detached units. And as I mentioned earlier, those are smaller buildings that don't necessarily get individual design. Certainly the builders probably have some people doing design of them, but there's a lot of single-family detached units. 6% are single-family attached, so that would be like townhouses. 5% would be mobile homes, and then the balance would be multi-unit buildings, multi-unit apartment buildings. So if I'm doing my math correct, that is somewhere on the order of, let's see, 28 or something percent of the housing units in the United States are in multifamily. And look at data from Canada, and Canada is actually pretty similar in terms of percentages. I think they're a little bit lower in the single family detached. I think they were in the 50%, but Canada is probably not much different from the US. A little bit harder to find data from worldwide, but this kind of gives you a perspective of what we're looking at. And I put these pictures here to the right just to kind of stress the challenge in the residential sector, and that there's so much variability in what we're dealing with. We have large apartment complexes in big cities. We have townhouses. We have single family homes. We have 2 or 3. We have duplexes. We have low story apartments, etc. The variety is massive, and that's one of the challenges I think the residential building sector faces, is that it's hard to do a one-off and do it well, and so just dealing with and trying to serve all of these different pieces of the residential sector is a challenge. In terms of how much money we spend, now the data is pretty old from DOE. Back in 2015 is their latest ones they put out, but we're looking at about $1,800 per year in annual energy costs. I'm guessing that has gone up with costs going up here, but it's not an insignificant amount of money that we spend, and it certainly ranges across the country. Where many of you are in New Hampshire, I saw the numbers were something more along or New England at least, the numbers were more along the lines of $2,400 a year, just because it's a colder climate. So it certainly is quite a bit of variability. It varies on the house size, etc. But this is, bottom line, it's not an insignificant number in that. A few more residential statistics. There's a lot of construction spending. The number I saw was 700 billion, and I think that's a big number. That probably encompasses a lot of ancillary things and appliances, etc. But bottom line, it is a huge economic driver in this country. And in terms of how many are being started, the latest data I found was in 2020, and there were about 990,000 single-family home starts and about 390,000 multifamily home starts. And this, what does that say? So, I said there's about 128 million units that are out there right now. We're building on the order of, say, 1 million new ones every year. Bottom line, if we want to deal with improving our building stock, we're going to have to deal with existing buildings. So that's less than, say, 1%, or on the order of 1% of the building stock is built new every year. So some of that is replaced, some of that is additions. But bottom line, we're not changing our existing buildings very frequently. So that's just something to always keep in mind, dealing with the retrofit market. If we want to improve building performance, that is going to be a big one where we have to address. Now, this chart that I'm showing is the number of housing units by year of construction. And this just reinforces what I was just saying. You can see that, of the housing units out there right now, A lot of them were built in the 1970s to 2000s, which doesn't seem that old to me, but they're going on 40, 50 years, and they probably, I was talking to Paul earlier about Drew Carley's talk last month. Do we just tear these things down and start new? Probably not. That's probably not the best, most efficient way to do things, cost-effective way to do things, or energy efficient, carbon efficient. So dealing with all of these older homes is going to be a big deal as we move towards a decarbonized future. You've probably seen some of these data, but just reinforcing this idea that the residential sector is a biggie with residential end use. We estimate that it uses more energy than the commercial sector. Industrial and transportation do use more, but residential, with about 21% of energy consumption in the United States, certainly nothing to, even though each individual house might not seem like a whole lot, when you add them up in sum, it really makes a huge difference. So if we want to tackle our energy challenges, our carbon challenges, certainly the residential sector is one we have to address. And this is a worldwide one that I find this one very interesting, this data from Department of Energy as well. So this is over time, and these are projections. And on the left side is a chart of energy consumption, and on the right side is electricity consumption. And the yellowish chart, yellowish line was the residential. So in the left chart, it's the second from the bottom. And you can see it's projected to continue to rise, more so than even the commercial sector. We do see these large predictions of industrial and transportation. But what's really interesting to me is the right side, is the electricity consumption. And why is that? Why do I find that interesting? Is that since there is such a push to electrify heating in buildings and to move away from fossil fuel burn, you can see the residential sector sphere is really projected to go up pretty significantly. And so the impact on our electric grid, on the stability of our electric grid, is such a big deal, and dealing with the residential sector is a big one. So I just find that very interesting that, as we're pushing electrification, how do we do it well in residential is going to be really important for grid stability, for just overall how we do things. Now, how do we use energy in residences? I always, when we give tours, we have a facility that I'll talk about in a few minutes here about, I always ask people, where do you think you use energy in residences? And this audience might know it very well, but the answers I often get are frequently things like, oh, it's my lights, it's my TV, it's my refrigerator. And those are good answers, but I think that the key takeaway I try to convey to people is really in houses, there's a big three. There's space heating, there's air conditioning, and there's water heating. And those are really the big three. Lighting comes in fourth, and appliances, no doubt. And plug loads have certainly increased. There's no doubt that plug loads have increased in their energy usage as we're plugging more things in. But still, the big three are the ones we really need to address: space heating, air conditioning, and water heating. And obviously, depending on where you live, in New Hampshire, certainly space heating is going to be a pretty significant portion. In parts of California, water heating is actually the top one, because there's not much need for space conditioning, whereas if you get to South Florida, air conditioning would be a big one. So it's certainly location dependent, but regardless, really these are the big three that we have to consider if we want to decrease energy consumption. But finally, this is a busy chart, and I'll try to explain what I'm talking about here. Is at ASHRAE members, yes, we're definitely interested in energy, but indoor air quality, indoor environmental quality is a huge part of what we do. We really want to ensure that the built environment is really a good environment. I tend to say a healthy environment. People shudder at that because we're not health professionals, most of us. Some of us are, but we want to create the conditions for healthy living. And you think about how much time we spend in homes, and it's a lot. It's a lot. So the data I pulled from a paper that was recently published in 2020. I believe the data was actually pre-pandemic, so things have certainly changed since the pandemic. But this is the time that people are away from homes on weekdays on the left and on the weekends, and each one has 4 charts, and it really is dependent upon age. So you see the top left chart. What this is saying is that about 12% of people under 25 basically stay at home 24 hours a day on weekdays. You know, they don't leave the house, and you can see this distribution. So the bulk of them are away for like 10 hours, and this is maybe they're going to school, for example. And you can see even the other age groups, 25 to 54, 55 to 64, they're probably going to work, so they're away from the house 12 hours, 11 hours. Age 64, though, the large percentage of those people stay in their home for a large fraction of the time. On weekends, you can see that hump is gone because people aren't going to school or as much or going to work. Bottom line from this data is that we spend a lot of time in our homes. And so really ensuring a good indoor environment is so important. You know, we have a great appreciation of, you know, indoor air quality, indoor environmental quality, say in offices. We want to make sure it's a very productive environment, or even schools. We have that appreciation. But you think about all the time we spend in home, even if we're relaxing, you know, it does have an impact on our well-being. And so this is just, you know, drives home that idea is we should really be thinking about the indoor environment in homes, because, you know, we spend so much time there. That kind of gives you just some statistics. Now I want to talk about what I see as challenges facing a residential building sector from an HVAC&R perspective. You know, there's certainly challenges in terms of interest rates for mortgages, and I would say finding, you know, supply chain issues and finding qualified workforce are really issues. I want to talk a little bit more about what I see as the technical challenges, and what I'm pulling this from is our committee has really been thinking about this, and we're really trying to formulate ways to do that. So a lot of this is what I'm hearing from them, but a lot of it is certainly my interpretation of it. As with many buildings, and I'm sure you're facing it, this idea of electrification and decarbonization is really a biggie for the residential sector, in addition to for every building sector. I was just reading the other day that my county, where I live in Montgomery County, Maryland, they're going to mandate by, I think it's 2027, that all new homes, new buildings will not have fossil fuel combustion. There's exceptions for, say, restaurants and maybe some industrial type of buildings that really require it. But, you know, I thought that at first I read, I'm like, oh, that's way down the road. But then you're like, that's not that far away, you know, and to require electrification of heating in the next 3 or 4 years, it's going to be a big switch for the industry. Now, I used to say electrification of buildings, and then somebody said, well, haven't buildings been electrified for many, many years? And so more recently, I've been saying electrification of heating. And so some of the big challenges that I see the residential sector is facing is, just say for retrofits, if retrofits mandate this switch to electrical, how do you replace a furnace with a heat pump and do it properly and do it so that the consumer is happy with that? Can heat pumps meet the customer demands in all climates? You know, certainly in some of the colder climates, there are concerns, and there's certainly people that don't believe that heat pumps can necessarily meet heating needs in colder climates. Can we do that? And then how do we properly install and maintain, I'm going to say, heat pump water heaters? Now, admittedly, I have a background a lot in water heating, so I think a lot about the water heating sector. You know, I recently, just a personal anecdote, tried to get a new water heater, and I called around plumbers and nobody wanted to install a heat pump water heater. I mean, I had great confidence that these would save me lots of money, but they just didn't want to deal with it. It's just more complicated. Just stick in an electric resistance tank. That's the way to do it for them. But so how do you, they just are more concerned with that. So conveying, you know, how do you install these things properly and how do you maintain them? You know, I think there's more can go wrong with a heat pump water heater than a conventional electric resistance water heater. So those are some of the challenges that I see in electrification. The next one is this idea of indoor air quality. So energy codes are getting much more stringent, requiring much more airtight structures. And I think that there's this, you know, whereas there was a sick building syndrome acknowledgement for commercial buildings, say in the 70s and 80s, when we were trying to tighten buildings, I think that this is starting to become at the forefront of even our residential buildings. There's been a lot of studies about the impact of, you know, combustion appliances in homes, or cooking in homes, for example. And as our homes are getting more and more airtight, we're bottling up all of those contaminants. Add to that, I would say the greater appreciation by the public of the importance of indoor air quality because of the pandemic. I think that it's much more at the forefront of people's minds with the pandemic that we need to bring in outdoor air. We need to keep our air turning over. I would like to think that all of us ASHRAE members have appreciated IAQ for many, many years, but I think the public at large has this greater appreciation of indoor air quality because of the pandemic. But what I see as sort of the real challenge is how do we improve the IAQ cost effectively? I think you'll get pushed back a lot on adding fans and the energy costs, fans costs, and I will talk about that in a second here. Some of our research on that, but it is a big challenge. Balancing that optimization problem. You want to keep a healthy environment, no doubt, but how do you do it cost effectively? Another one that we're seeing that has come up a number of times is these low GWP refrigerants. So, we have to start phasing out older refrigerants that have a high global warming potential. And the questions really are still out there: which refrigerants are going to make the most sense for residential applications, ranging from your refrigerator to a heat pump, air conditioner, heat pump water heaters? Which ones make the most sense? I think there's still a lot of research that's going on and a lot of questions. And one of the big questions that pops out is some of these new refrigerants have some degree of flammability. How do we assess them? So they're not as flammable as, say, methane. Some of them, I mean, propane is a really good refrigerant. That's pretty flammable, but there's others that are mildly flammable. And there are really some challenges on how do you measure them? How do you assess how flammable they are? And how do you assess what will happen when they are installed in homes? And how do you best design a system that uses a refrigerant that is mildly flammable or flammable? So that's, I think, one of the big challenges that the industry is facing. I mentioned this a little bit. We have a lot of buildings that are going to be around for a long time. So I think that improving performance of existing buildings is really going to be a challenge for the residential sector. Now, I think that if you look at most buildings, for example, I had an energy audit done in my home, and maybe some of you have as well. And the first thing the auditors will say is, well, you need to add insulation and you need to make your house more airtight, seal up all these things. And that's probably a great suggestion. I think doing so is really challenging. And in general, envelope retrofits, building envelope, are great opportunities for energy savings and actually great opportunities for thermal comfort improvements and air quality improvements, building performance in general, but they're really challenging to do it well. And it's really challenging to do it well at reasonable costs, to have consistent ways to do it. So in my mind, is how do we tackle energy, retrofits of buildings in a lower cost way, in a less intrusive way? If you had to redo all of your envelope, boy, that would be a pain in the neck. And so how do we do it in a more effective way is really a challenge, I think, for the building industry. One of these, I think this might be my last one on the challenges, and this one came up a few times, is that, the residential building sector, because it's such a discrete or diffuse sector, you have, small companies installing your HVAC and another one installing the doors and another one installing the siding, and there's so many players and most of them are smaller entities. We really have to rely on standards and building codes to really ensure quality. Whereas sometimes maybe a bigger commercial building, you'll have an engineering design team and you can really analyze things very well and maybe justify an innovative solution that will still meet the intent of energy codes, safety codes. With the residential sector, there's usually not the money on, say, the single family housing side to really, do a lot of, design analysis and design work. So we really rely on standards and codes to ensure quality, to ensure safety. Now, the challenge there then is, if you're a code official, you don't want to see things that deviate too much from what is in the code. And so finding ways to promote innovation, innovative solutions while still following codes is a challenge that I've seen come up raised by a number of people. How do we show that an innovative solution might improve indoor environmental quality, decrease energy consumption, it still keep the people safe and still meet the intent of the code? And that's a challenge I think the residential sector faces, especially when you don't have as many, say, full-fledged design teams working on each house. So what I want to move into next is some discussion of, I talked a little bit about a lot of these challenges. I do want to talk a little bit about, some of the research that is going on. We talked a little bit about this idea of innovation. How do we promote it? There is a good deal of research going on. a lot of the research might be in government labs like ourselves. As you've probably seen quite a few times, the construction industry doesn't have a huge R&D budget, and so, but that doesn't mean they're not doing their research and development as well. But there is a lot of innovation in there. I did want to talk to you a little bit about some of the stuff that we've been doing at NIST. It's actually, some of the data I'm going to show is a little bit old, but it kind of highlights some of the challenges we face and some of the things we're thinking about to try to help the industry achieve these goals of decarbonization, of improving building energy performance. So what I want to talk about is what we call the Net Zero Energy Residential Test Facility. And this is a picture of it. And if you're ever in Gaithersburg, Maryland, let me know. I'd love to give a tour of this. We give lots of tours of this. And this is a house on our campus. It's right outside my building. And yes, it looks like a house, but it's actually a laboratory. And it's an office building, or truly, it's characterized as an office building, but it is designed to look like a house. We have a real architect design this. It was actually Building Science Corporation from Massachusetts was the architect of record for this. So hopefully it does to you look like a house. And that's one of the things we wanted to do, is we wanted this to be a very typical house that one might see in the Gaithersburg. So we're outside of Washington, D.C. And I think if you saw this house in the Washington, D.C. suburbs, it wouldn't look out of place. And that was really one of the goals of this, is to be a showcase to show people that you can have energy efficiency, you can have a really high performing home, and it doesn't have to look like a science project, that it can really feel comfortable. So you can see on the front there's a lot of windows. If you walked in this house, there's actually a good amount of light, so you don't feel like you're in a thermos bottle or anything. And it has all the features that you would see in a house. So it's a 2,700 square foot living space, which at the time was about the average size of a new U.S. home. It's got 2 floors. It's got a basement, about a 1,500 square foot basement. It's got 4 bedrooms, so it would be a typical house, and 3 bathrooms, garage. You have it. So it does look and feel, and you walk into it, it's got an open floor plan. It's got all the features you might like. And I think that's one of the things we want to show people when we walk them through, is say, hey, this doesn't have to be a weird house. You could still reach this idea of energy efficient. So our goals, and when I say net zero, what we mean, and just many of you may know that term, but the way we're using it is over the course of the year, it generates as much energy as it consumes over the course of the year. And so what we wanted to do just initially is, let's demonstrate that its home can meet that net zero operation. And we did all sorts of modeling, and we had great confidence that we would meet it, no problem. But we'll talk a little bit about results. And we wanted to, so really just to prove out, just to show, hey, we could do it. But more than just that, we wanted to actually use it as a laboratory, and really serves as a test bed to evaluate energy efficient technologies and approaches, and including their impact on the indoor environment. So it's really a nice place for us to do this measurement. So I said earlier that one of our things is measurements is one of our big things at NIST. And so we really tried to look at different ways to measure performance of all sorts of different systems and their interactions, because the interactions, as homes become more tight and more we're really squeezing the energy budget, all the interactions between these systems really start to have a big impact. So measuring those and getting really good data on that is really one of our goals for this. So 5 steps to net zero I have here. So the first thing you really want to tackle is, a well-insulated and airtight building envelope. So that picture in the upper right, it's a little blurry on my screen, sorry if it is on yours too, but this house was actually wrapped with this peel and stick membrane all the way from the ground, the foundation, all the way to the peak of the roof. So this thing is super airtight with this construction. And then all the windows are really well sealed as well. And the insulation is really, really high. So as I said earlier, heating and cooling are some of the bigger loads we have, energy demands in a home. So the way to tackle that is really to build a good envelope. So that's really step one, is decrease those loads. Second one is, I say place the equipment within the conditioned space. That's sort of kind of this no-no in homes. You don't really want your air handler out, in your hot attic or somewhere in your garage, for example. Ideally, if you can do it architecturally, place the equipment within the conditioned space, meaning the heating and cooling. And we were able to do that because all of our insulation goes all the way up to the peak of the roof. So if we have any mechanical equipment in the attic, it's still within the conditioned space. Now, when you build something that airtight, what's one of the challenges? And it's sort of, we need air to breathe. We need fresh air. We need outdoor air. So in this house, we can't just depend on leakage going through cracks because the house is so tight. So we really need to provide this controlled ventilation, just like you might do in a commercial building. These homes now are getting so tight that you really need to do that. Now, this gives us a lot of advantages. You can do it in a very smart manner and an engineered manner, providing very controlled ventilation. We'll talk a little bit about that in a second. And once you tackled all this, really select the best appliances you can. The heat pump we got was really energy efficient. The water heater, the dishwasher, everything, clothes washer, etc. So selecting very energy efficient appliances. And then once you've done all of those things, get your loads down. That's when you then think about the renewables. Some people, it's kind of this glamorous thing to put PV on your home, but really, I would contend that's probably the last thing you want to do. When we built this house about 10 years ago, solar was still the most expensive piece. Now, costs have come down dramatically, so the economics may have changed. But I think one of the advantages of doing these first 4 steps is you really provide a really good indoor environment. That well-insulated envelope, airtight envelope, will decrease drafts, and will make it a more comfortable house. And I think it will make a more resilient house. And that's another thing that we talk about now a lot more, is resiliency. If the power goes out for a while, you're okay. We had an example where, in the middle of summer, we had a power outage, and we had these tours of some higher ups coming through, and we were worried because the power was out for about a day, but the temperature didn't drift that much. I mean, it may have gone up from a set point of 75 to around 80, but it really wasn't that bad, even though it was in the 90s outside. A well-sealed house like this is a very resilient house. So there's benefits to all of these first steps that you may not get just by slapping photovoltaics on the roof. So talking a little bit about the envelope, there's a lot of data here, but bottom line, so at the time we had to conform to the 2009 IECC. Our walls at the time were about 3 times as well insulated as the IECC called for. Windows are about twice as good. The roof assembly was about twice as insulated. And the way we had to do this is our walls were thicker, so we used 2x6 construction, and then we had exterior insulation, as you can start seeing going up there, and that's foam insulation. We had about 4 inches of foam insulation on the outside. Challenging to do, there's no doubt about that. It's a challenging thing to do, but by doing that, we really created a minimized thermal bridging, and really created like I said, the thermos bottle to really keep that heat in or keep the heat out in the summer. And being so tight, we had 0.63 air changes per hour at 50 pascals. It was a really, really tight home when we built it. And actually, we've been taking tests periodically over the years, and that number hasn't changed much, which is a testament to the construction process, that really things haven't changed too much. The heating and cooling systems, one of the things, because this is a laboratory, we put a lot of different technologies in there. We have a conventional split unit, and we used that for the first year of operation. But this thing was, really high SEER level. I forget what it is right now, or HSPF. One of the things we needed, though, is to make sure we had dehumidification. In our climate down in the Washington, D.C. area, we have to really worry about that in the swing seasons in the summer. And this heat pump needed to have special dehumidification cycles as well. So we had got that. We also had a multi-split heat pump system installed into it. We could do that. We also have a small duct high velocity system that could be used in there. So all sorts of different duct work that we could swap out. And then I'll talk about in the second, geothermal wells at the bottom. This is something we have. We have 3 geothermal wells around the house, a vertical borehole. It goes about 150 feet straight down, a horizontal U-tube in the back that's about 6 feet under the ground, and then a slinky tube, which is in the front. So instead of having this large area that you need for the horizontal one, you coil all of the geothermal tubes in. We're going to be looking at these. We actually haven't used the geothermal system yet, but we're getting ready to run tests here shortly, in which we're going to use, I think, the vertical borehole and really evaluate the performance of geothermal. We have all these sensors in the ground for 10 years now. We're going to be able to use those. In terms of the duct work, we have also options there, conventional sheet metal, but we also have, and the ducts are at different levels, high distribution, low distribution, and we have all these controllers that we can valve off or zone out different ones, so we can really evaluate the effectiveness of different ones. That's one of the big things we've been looking at recently. And then we have this high velocity air distribution system. These are sort of these thin coils, and they're flexible, and they're really nice for retrofit applications. But for homes that are like this, that are so low load, there's some advantages. So one of the challenges we faced here is this home has such low loads that we really needed a small heat pump, and finding one was really challenging. We needed it to be small capacity, and I forget exactly what it ended up being. I think it was about a 2-ton unit we were able to get. It had to be really energy efficient, and it had to have special dehumidification capability. So finding the right equipment for such a low load home was challenging. Mentioned that because this house is so tight, we needed ventilation. And so we had a dedicated duct system for balanced mechanical ventilation. Now, this is an extra cost, there's no doubt about it, but we really think this is sort of the gold standard of the way it should be done. So there was separate, whole separate duct system for ventilation air. We had a fan system that, continuously pulls air for the outside and then deposits it inside. The air is pulled from the bathrooms, and then the outdoor air is inserted into the bedrooms and the living area. It's a heat recovery ventilator, so it's estimated to be an 80% recovery of heat. So any of that nice warm air that we're dumping out in the winter, we're estimating to get about 80% of that heat recovered from that incoming air. So that's kind of a nice system. Recently, we've been testing an energy recovery ventilator that's also exchanging moisture. We're debating, we weren't sure which way to go. The architects were kind of going back and forth, so we're curious to see what that data looks like. Our ventilation rates in that first year exceeded 62.2 standards. And the reason why is because this fan had discrete settings, 1, 2, 3. Setting 2 didn't meet 62.2, setting 3 exceeded it, so there wasn't a perfect match. So we actually were bringing in more ventilation air than we needed to by 62.2, but we didn't want to go below 62.2. The renewable systems we have on the roof, which is a 10 kilowatt photovoltaic array. Now this is a big system, there's no doubt about it for a home. But we had the roof area, and we had the good fortune of being able to site this house very well. So this faces directly south, so it's really optimally placed. And there's not many trees out in front. You can see there's ones on the side that might shade, but really we have a very clear view of the sky, which we're lucky. Not everybody has that luxury. We also have, well, I should say with the photovoltaics, it's a grid-tied system and there's no local storage. We did have capabilities to plug in an electric vehicle, but we've never used that. So any excess electricity, we just dump it back into the grid. And then when we need electricity, we're not generating enough, we're pulling it back. We also have solar thermal. For water heating. We also have two systems on there. There's 4 panels. A normal system would only have 2 panels, and that's on the porch roof there. We've only used 2 of them, and what we used that initially was to preheat water and then goes into a 50-gallon heat pump water heater as a backup. So in the summer, we could certainly get enough heating from those solar panels. That was fine, but we definitely need some sort of a backup. Last thing I want to mention is with houses, people really matter. So you can't forget about people. And this is a laboratory, so we didn't have people living in there because the other problem with people is people do random things, and we wanted to control things well. So people use appliances, people give off heat, moisture, and contaminants, and they require thermal comfort. Those darn people, right? They tell you when it's not comfortable and they mandate. So what we have here is computer-controlled usage of, say, showers of all the appliances on a regular schedule. We have these resistors in the rooms that generate heat just as people were. So if people were in the bedroom and they're sleeping, we put off heat as they would. And then we have sensors in the rooms that tell us whether or not we're keep us honest. It's easy to reach net zero, just turn off all the heat and air conditioning, but these sensors would tell us whether or not it is comfortable. So results. So this chart, this was way back in 2013. Whenever you see a red line going above 0, that means that we generated more electricity that day than we consumed. Vice versa going down, that means we consume more energy than we generated. And this blue solid line shows sort of the energy in the bank, the cumulative from the start. So we started in July, and in our climate, summer is pretty good. Yeah, we do have a lot of air conditioning needs, but there's a lot of solar. And so we were doing really well. Come around mid-November, though, things started turning south. It starts getting, the heating loads are dramatic, so we have to spend a lot more to heat, and there's not as much sun. So, this time of year, really bad. So we really plummeted there. We were getting nervous. I said we did all those calculations that we were confident we're going to reach net zero, but come
April 1st or so, we were at this low trough, and I wasn't sure we were going to make it. But spring was really nice. Spring, the climate gets much milder, so not as much heating and cooling needs, and the sun is just much more available. So we ended up having a 7% surplus in energy generation over the course of the year. Winter was really challenging to meet those energy demands. We projected a little bit more, so we were a little bit like, what did we do wrong? But some of the lessons learned, this is sort of this aha moment. Photovoltaics don't perform well with snow on them. This was an unusually snowy season this year. So we're covered by snow for 38 days, which maybe in your climate, you're laughing at that. That's nothing. But for us, this was a very snowy. That's over a month that we're losing. And one of the challenges, this is a well-insulated roof, so there's not much heat coming up from the house to melt the snow off the photovoltaics. It's a good thing, but it's one of the implications of such a well-insulated home. For this system, the way the PV was designed, partial coverage meant minimal output. So if you're familiar with photovoltaics, these rows here, there's 4 rows, and they're actually connected in series. So if you block off 1 or 2 of them with snow, that really takes out pretty much the entire row. So in this case, where I'm showing about maybe 3/4 of the photovoltaic array is covered, that doesn't mean that we get only 3/4 reduction. It's pretty much the entire thing is knocked out, even in this situation. So we pretty much had to wait till everything melted before things were working. Now, newer installations, I think, get around this challenge, but at least in this one, which was the standard way to do it, we really suffered a lot from missing out on PV. Another thing we learned, good heat pump, bad thermostats. We spent a lot of money on a really good heat pump, but our $100 thermostat was just sticking it into resistance mode a lot. We know the heat pump could have met the heating load. There's no problem, but the way the thermostat was programmed, it was just based on time. It just would automatically kick things into a resistance mode, even though the heat pump was doing it. And what that ended up doing is a lot of our colder times, we spent a lot of time in a very inefficient heating mode. And this was really one of the big causes of problems, why we didn't get as much energy surplus as we thought we would. So this is just one of those lessons.
Just a question there, Bill. Is that because the thermostat didn't anticipate that there was a lag on the heat pump in terms of coming up to temperature? In other words, it wasn't intelligent enough to understand the relationship of heating to time?
That's correct. Yeah, all it did was it said, okay, if the heat pump is running for, I think it was 30 minutes straight, let's automatically go into resistance mode. Even though it was maintaining the temperature as necessary, it really wasn't smart enough to say, okay, we're doing fine, let's leave it alone. It just was purely a time-based thing, and it just kicked in the resistance elements.
Yep.
Yeah. So, next one, ventilation air. So there's no doubt it has an energy impact, but you really can't do without it. I mean, you need ventilation air. You need to be able to breathe. You need to get the odors out and get the moisture out. We estimated, we did a really good analysis of combining our heat pump and the COPs of our heat pump and all the ventilation air that we brought in. We estimated that about 15% of the total home energy consumption could be attributed to the ventilation air. So that means the additional thermal load brought on by the ventilation air plus the fan energy needed to move it. So that's a pretty significant amount. And about 1/3 of the energy used by the heat pump was really for the ventilation air. So once again, it's necessary, you have to do it, but how can you do it more efficiently is always a challenge. It definitely has an energy impact, and we were able to really get some good data on this. Now, the question I'm always asked is the economics. So this is great. You save on your energy bills. You don't have to pay a utility bill, but how much does this cost? So we did a lot of cost analyses. We worked with estimators to kind of get really good data as if, what if this house were built in a subdivision? How much would it cost compared to, say, the IECC? And we did a comparison to the 2015 IECC code compliant home. Used a lot of data sources, so there's really a range of costs, and these are probably outdated still. And these are all without government incentives. So the estimated increase was estimated to be anywhere from like 107,000 to 142,000. We're ballpark at 125 if you want to take an average. And this is with a code compliant home being around 520,000. So it's about a 25% premium. So certainly there's still room to grow here in terms of decreasing costs. The biggies were the building envelope increases. We ranged from 50K to 75K because there was so much more insulation, so much more wood, in those. So that was really one of the big places where the costs were. The systems, the hot water system, HVAC, and renewables also had a big impact. The renewables initially were the big increase, but with PV prices coming down so much, they actually were. I think they started to not be as significant as some of the envelope work, but still it is an expensive PV system. Once again, I said these do not include government incentives. If you start adding in government incentives, these numbers start looking a lot better. But bottom line, it's depending on how you define cost effectiveness. Maybe you could say it's there, but there's still work to be done in terms of improving costs, no doubt.
I mean, the aggregate there, Bill, we're looking at roughly 50%, aren't we? I mean, in aggregate, if I just kind of look at those numbers.
Well, the 107K to 142K in the first bullet, it encompasses the envelope and the systems as well. So
it's lower. It's more like 40%.
Yeah, so it's about 125K compared to 500K. So it's about a 25% premium, I would say, if I'm doing my math correct.
Okay.
Yeah. So it's still, like I said, still a ways to go. We still have work to be done. One of the things, at least in our area, is we expect the envelope costs would be the increase would be lower because right now in Maryland, the standard way to build is with 2x6 construction. So I think the learning curve would decrease some of the costs. So it would be interesting to do this study again, since it's still 2015, 2016 numbers. So as a quick follow-up, we made changes. We ran for a second year. We did get 16% energy surplus. A lot of the changes were related to that heat pump issue, that thermostat I was talking about. So we made those changes, and that was good. Some of our recent activities, air distribution. So this low-load home, I mentioned we have a really small air conditioning heat pump. It just doesn't run a whole lot and really doesn't mix things very well. And there's very significant stratification from ground level to upper level. So we've been looking at different ways to distribute the air. It doesn't make sense to get two systems, as many people might have in a two-level home, just because the loads are so darn low. The systems would not run very often. So we have a single system, but it still deal with major stratification. We've done some in-depth examination of thermal comfort. That picture on the right is a whole bunch of stands to try to estimate the variation. Turns out there wasn't much, and I think that's a testament to the well-sealed envelope. They're really, it's very, very well, very uniform in terms of thermal comfort. We've been looking a lot at water. So there's been a lot of discussion recently about water and energy efficiency measures, such as low fixtures. What impact do they have on water quality? With such low flow fixtures, water is sitting in our pipes a lot longer. So we've been trying to look at that, the impact on water quality. Ventilation, I talked about the huge energy impact. We're looking at things like demand controlled ventilation, sensing, we've been inserting CO2 into the home and seeing if demand controlled ventilation has worked. And then one of the big things we've done recently is indoor chemistry. In terms of indoor air quality, there's a lot of interesting stuff that goes on in the chemistry of intermediate products, and a lot of stuff that goes on. And for example, we brought in like simulated wildfire smoke. What happens when smoke gets into a home and makes all these chemical reactions, and that's been one of our focus areas too. So stay tuned on any of that. If you want any more information, here's our website. Paul will share these slides, or just search NIST Net Zero House. We have lots of data, all of our publications, and we'd love to get any feedback from you on that one.
All right.
Okay, so go ahead.
Well, I was gonna ask, how far? What are you gonna go now? I mean, we get near the end here, or do you? Because I got questions.
Sure. A little bit longer. Let me just finish up real quick.
Yeah, okay, go ahead.
ASHRAE and the resident, and I'm going to zip through this. I put a lot of slides just in case we had time, but I'm going to zip through this. I do serve, as I mentioned, ASHRAE has a residential buildings committee, and this is a lot of words, and this is from the rules of the board. Why do we exist? This is our scope. Committee shall be responsible for identifying major residential trends impacting the practice of HVAC, and R. So we have this committee, reports to Technology Council, and really our mission is, what does ASHRAE need to be doing in the residential space? What are the major issues dealing with residential? And so that's really why we exist. We have a team of about 15 people, and we rotate every 3 years. We get people have serve 3-year terms and try to make activities on what ASHRAE can do to help the residential space. Now, the history, and this is a lot of stuff, I'll try to zip through this. Bottom line, it's a relatively new committee. It officially was formed, the president at the time said, let's really look into this. So he formed an ad hoc committee to look at what we need to do in residential. And this residential buildings committee was established in 2015. So it's a relatively new committee in terms of ASHRAE, and we've done things like stakeholder workshops and stakeholder outreach. I'll talk a little bit about that. This ad hoc committee, when it was formed by the president, had some select recommendations, and there's a nice report that came out to establish our committee, to reach out to residential stakeholders, to be better engaged there, give greater importance to the residential sector in conferences, and then support research, and then engage really with the technical committees and the standard project committees to identify residential topics in the handbook. So we're not doing it, we're trying to coordinate work with the technical committees. We have a nice website. I would point you to this. Has a lot of it has our committee stuff, which may not be very interesting, things like minutes, but we do have all these residential resources, and I will talk a little bit about some of them. And then on the bottom right, there's issue briefs, and I'll mention that as well. But let me just dive in. I think it's a nice resource for people looking for residential information from ASHRAE. Some people may not appreciate all the products that ASHRAE has in the residential space. I'll start with standards. One big one is the standard 62.2. Some of you may be familiar with 62.1, ventilation and indoor air quality in commercial buildings. This is a corollary for residential. And a lot of people in the building industry know ASHRAE. If they're in the residential industry exclusively, this is what they think of as ASHRAE. This is what they think the only thing ASHRAE does is this standard, because a lot of the programs require compliance to this ventilation standard 62.2. So that's a big one. But there's a lot of others. 90.2 and 90.1 is sort of the governing one for building standards and building codes for commercial buildings. But 90.2 has recently tried to become more of a stretch code. And one of the things that's interesting they're looking at now is putting a carbon metric in there. So in terms, not just an energy standard, but they're going to be putting carbon, which is becoming more and more of an issue. So standard 90.2 is a biggie. 15.2 is a safety standard for residential. And there's so many others, standard methods of test that govern performance of furnaces, boilers, heat pumps, water heaters, air cleaners, ... There's so many standards that ASHRAE is involved in related to residential. Another one is guidance documents. The multifamily design guide was really, I keep hearing people saying like, oh, this is a treasure trove of information if they're designing multifamily homes, and then the advanced energy design guide for multifamily buildings. And that's really how do you get towards net zero operations. So there's some design guides, residential indoor air quality guides, another one. And then I think the epidemic task force efforts on COVID was just a really great example of how ASHRAE could serve society. What do you do in homes, and what are some good guidance on that? So I think that was another one. It's a really good example. And then finally, research handbook training programs are all ASHRAE products. I'll put in a plug for the winter meeting. If anybody's able to go down to Atlanta, we have a lot of programs related to residential. There is stuff strewn across the handbook. Unfortunately, sometimes it's hard to find with residential, but the handbook does have a lot of good residential themed efforts. And then there's all sorts of training that are offered on topics, and we're trying to work on that. How do you improve it? So better training, for example, on 62.2 is on our radar screen. We also put out these things called issue briefs, and this is done by the committee, and these are relatively new, so there's not a whole lot of them, but these allow us to really highlight a topic of interest in the residential sector to ASHRAE and suggest actions for ASHRAE to take. So the two that we've completed so far is one on wildfire smoke hazards. There's been so many questions, especially as wildfires in the West have burned. What do you do in a home? You don't just bring in outdoor air when the outdoor air is bad. So what do we do that? And kind of the guidance here is that ASHRAE should really develop better guidance documents, and we're working on that. And then another one is the impact of ventilation IEQ on the sleep quality in bedrooms. This has been another area of people have been thinking about a lot. You really need to improve IEQ and to ensure better sleep and better health overall. We're working on another one right now that's on working from home. A lot more people are working in homes, and what impact does that have on ASHRAE? And that one will hopefully come back. But this is a good way to highlight emerging issues. Stakeholder needs report. Let me zip through this for the sake of time. We reached out to a lot of the key stakeholders in the industry. One thing I will say, there's so many of them, and that's one of the challenges in residential. There's so many players that are involved. Some of the key things that came across was, ASHRAE research is really important in the residential sector. There's probably a need for more research, but not as many organizations can fund it. All the ASHRAE standards were great. Continue with that. Coordinating activities across all of these stakeholders is really a good ASHRAE role, so that would be a good one. The other one is explore techniques to let ASHRAE people know what ASHRAE has to offer, and that's almost, this is one of my goals here, is to let people know what ASHRAE has to offer in the residential sector. And I'd love for your feedback to figure out how do we get the word out better on what ASHRAE has to offer. And then just continue to take a leadership role structurally for ASHRAE, and we'll keep working on that. So this is kind of one of my final slides here, but one of my purposes for coming here is we're really interested in understanding what ASHRAE chapters want to see from the society related to residential buildings. We did a lot of this work on the stakeholders, say the industry organizations, but we'd love to hear from all ASHRAE members as well to understand where are we missing the boat. What are the big gaps in residential buildings where you might want to see more information from ASHRAE or more work from ASHRAE?
Well, one of the basic ones that we could find out, Bill, is the bulletins that you just referred to, that you put out bulletins periodically. How do we get on a mail list for notification of those bulletins, for example?
Yeah. There is a listserv, which my understanding it's not very well used, but there is a listserv. But that's a really good idea. How do we get the word out?
If you want to send information to our chapter, for example, I'll distribute it to our members and make sure that they are on that list, for example. ASHRAE does a fairly good job with its journal, and it does a fairly good job communicating. But sometimes the committees themselves, like, the residential building, doesn't necessarily get into that distribution medium, if you know what I mean. So
sure.
So even a short circuit where you just send to the chapter lead or to the chapter or to one of us here, to me, for example, I will push to the chapter.
That'd be great. Yeah.
Now, the other question that comes up, and it's come up a lot, is yes, you did this building, this test facility. I get it. It's great. It's wonderful to see it can be done, but it is a new construction where you did everything right. The very typical thing we run into here in this geography is an existing building with, for example, fossil fuel-based hydronic heat. These are, baseboard heat, where you have hydronic being run by fossil. Now, in many of those applications, retrofitting with ductwork to do hot air is near impossible, if not impossible. Do you have any thoughts about how do you replace the old oil burner in the basement of a home that has hydronic heat, which delivers heat beautifully, but kills you in fossil fuel and emission?
That is, I wish I did have a clear answer. I have seen some heat pump systems that are, air to water type systems that theoretically could replace that furnace. And I guess you don't need the highest temperature of that water going through those hydronic systems. So maybe it could work. That is a kind of a classic challenge, and I've seen that in the New England area. People always bring that up as being one of the big challenges, is these fossil fuel boilers, replacing them. And I've seen some furnace technology, heat pump technology to do that. I don't know how well accepted it is yet, and some people here might have a better idea on that, how well they perform. Whether you can truly replace that with the heat, right? I think it's going to be really challenging to stick ductwork in any of these systems. Now, I guess you could go with these multi-split systems, these variable refrigerant flow systems, but that's an architectural issue. Then you suddenly have to put a head of a heat pump inside a room, and I know that turns a lot of people off. They're really efficient, and there might be really a great way to do it. So that could be an option if people are willing to deal with that. Now you could build structure around that in a home, like around the head of the system, but I think it's a challenge. You're absolutely right.
The other one that we run into a lot is just the envelope itself being extremely leaky and trying to, that one's fairly straightforward. But I got another question here about electromagnetic radiation changing with tight building exteriors. Is there any concern about electromagnetic radiation? You know, again, the buildings have been leaky, so we haven't really been that concerned about it. But as it tightens up, we've got indoor air quality concern. I thought it was fascinating you're talking about in the bedroom. Hadn't really considered that. And the VRF system you just referred to as well doesn't necessarily help you there because it's not an IAQ device at all. It's recirculating interior air. So as these environments tighten up, I think that's where you run into some of these issues.
Yeah, I think it's a big issue. How do you, a lot of people with ventilation systems, they might just have a continuously running bathroom fan, might be an exhaust only system. And just because it's hard, it's costly to do these systems. I mean, we had a large budget to do this. It was a research house. We could put in this dedicated ventilation system, but it's a hard thing to do and it's costly. And I forget what the first costs would be for it, but just putting on a ventilation, if you're mandated to do it, the easiest way might be an exhaust only system where you just have your bathroom fans running consistently, and do it. So finding ways to do it cost effectively and that they'll work, and the other challenge people always hear is if people find a way to turn all those ventilation systems off because they're noisy or they don't know if it's working or not. I mean, that's one of the challenges we've heard too, is how do you make it, you don't want to say take people out of the loop because people are critical to any building, so you can't say you take people out of it, but it's almost like you have to build and design these things such that they're very robust. In terms of electromagnetic radiation, I hadn't thought of that. So you're saying that, like some of these systems generate electromagnetic radiation that could be harmful, and maybe the type of, it increases the amount of that. Is that the suggestion?
Yeah, I think it's a radiation. It's just electromagnetic radiation was the concern. But let me switch you one more topic over to air source versus ground source. Do you have, I know you're experimenting with ground source. You've got different kinds of ground source there. The logic in me suggests, the engineer, the thermodynamics in me suggests the ground source much better way to go because the delta P or the delta T, whatever you want to call it, the lift is going to be much lower because you've got a 50-55 degree source. Capital cost a little higher, but do you have any thoughts yet on ground source versus air source?
Yeah, I think you hit the efficiency wise, I have very little doubt that it'll be much greater, much better than air source. In our climate, our ground temperature is very uniform at about 55 degrees year round. Perfect, great for, and we have a relatively balanced heating and cooling load. So in the summer, we'll be dumping heat into the ground. In the winter, we'll be pulling it. We think we're relatively balanced, so we don't have issues with even changing ground temperatures. But you're right, the capital costs are so significant. And one of the challenges in a really low load home is that you're not using that system a lot. And so if it was a really poorly insulated house that really you're running that heating system a lot, running the air conditioning system a lot, you would be, that difference in efficiency between your air source system and your ground source system would pay for itself quicker because you're using it more. But in this house, because you're not using the heating and cooling very much, you're not really gaining a lot from that energy efficiency improvement. So you're still stuck with that large capital cost. But there's certainly climates that I think that there's no way, I think ground source, if we can get the costs down, I mean, there are a lot of the colder climates, I think that that's really a great way to do it. So you're not just running in electric resistance mode like we were doing, and barely meeting the thermal load of the house. So I think that in certain climates, it probably makes sense. It's still just a very expensive first cost to any ground source system, and that's the challenge.
Particularly if you're drilling, if you're drilling. But the problem that you run into with air source is the compressor. For example, and I've got one here in this home I'm in, and the compressor is running really hard to try to pull air out of a 20 degree source, and that means vibration. So you're hearing it. You're hearing a lot of noise from it because it's working really hard trying to do that. The other part you run into, Bill, it seems to me, is the size of it goes up because you need more surface area to pull the heat from. I mean, it's a 20 degree source or a 10 degree source. You need a lot of surface area to get the heat out of the air.
Yep, definitely. And I think what I understand, these ground source systems, and maybe I'm a little bit out of my area of expertise, but my understanding is because of things like you just mentioned, they're not working as hard. They have pretty long shelf life. They don't have to replace them as much. I mean, you don't have to replace that outdoor unit. That ground loop is pretty uniform temperatures, and it has a pretty long durability. So that would be another question too. I mean, full life cycle costing of these things. If you don't have to replace them in 15 years, maybe you're better off.
Yes. One of the final questions I have here, I know we're running a little over, is the system that you put in, the systems that you facilitated there are really pretty high tech. This comes to the question of installation technicians. Do you see ASHRAE taking any steps or any movement to try to increase the level of knowledge associated with the implementation so that, as you found out, nobody wants to put in a heat pump water heater because they don't have the technical skill to be able to do it. The system you've implemented is fairly high tech. That's a system. That's a full feedback control loop system. What about the techs? What about the training? Is ASHRAE taking any steps in that area?
We haven't yet, but that's a really good point. I think one of our challenges with the Residential Buildings Committee is understanding that there's a lot of stakeholders in this. There's a lot, for example, AHRIs, the Association of Heating and Refrigerating Industries, I think that's what they are. But they sort of and what role is there and what role is ASHRAE's. But one of the things that's always been, well, let the manufacturers give that guidance on how to install things. But as things start becoming more interconnected, what you do with your heat, one of the things I've heard too is, okay, you put a heat pump water heater and that's going to impact your heating and cooling load. So these trades need to talk to each other. And so maybe that is an appropriate role for ASHRAE, where we're dealing with systems and interaction with systems, and you can't just let the HVAC person install our HVAC system and have at it and be because that impacts other things, and the heat pump water heater impacts other things. And so maybe that is an appropriate role for us as ASHRAE, is to kind of give that system level guidance. Certainly I think the manufacturers are probably in the best position to say how their specific equipment is installed, but maybe from a system point of view, that is something ASHRAE could tackle.
Yes, because what I find is the individual contractors come in. So you have the manufacturer, and now you have a rep that's repping the manufacturer, and the rep comes in, the contractor, the local HVAC contract comes in and says, oh, you need to just put in this, and leaves. They put in one piece, it could be a mini split, and then they leave. And that system tends to interact with other systems. And I found the same case in data center design as well. These systems all start interacting with each other, and you have a systems problem, and there's no systems owner for the situation, and it becomes complicated.
Yeah, and it's probably worse in the residential space, at least single family residential, than it would be in other building types. Because you're right, they just want to get out of there, and they don't want to call back, and they want to be done. But who is looking at the entire system? So that's a good idea for ASHRAE as a role.
Well, I'm afraid we're out of time. We could go on for some time here. I've got a lot still to ask, and there's still some questions, but I want to thank you, Bill, for being here today. And I might like to invite you back in another few months because this isn't a once and done thing. I think we're all learning together. I'm fascinated about the research work you're doing. I want to thank you for doing it. Somebody needs to do it. We need to find a way out of this trap. It's very easy to say we need to go to electrification. The issue is, how do we get there? How do we get there economically? How do we get there practically speaking in terms of feasibility? So I want to thank you for taking the lead on that, and look forward to staying in touch with you and working with you in the future to try to help us navigate our way through this decarbonization effort on the residential side and on the commercial side. These things aren't uniquely different. They're still buildings. It's just an issue of ownership, I think, as much as anything. So thanks again for being here, Bill.
Thank you very much, Paul, for the invite and coordination, and everybody for joining, and happy to continue discussion whenever you want, and appreciate the opportunity.
Thanks. Have a good day.
You too. Bye-bye.
Bye.